in this particular case, if I am coming to the last row, what is the last row? -1 means it is minus I1, this is plus I2, this is 0, this is I4 plus I4, this is I5 0, minus I6 which is equal to 0. This is the way of the preparation of the row-wise addition. Now in this case, if I proceed further, now I will copy these equations and I will try to organize this equation in the matrix form. If I am arranging these equations in the matrix form, how is the first equation? This row and this column is equal to 0 because everywhere we have 0. This is 0, this is 0 and so on. Is it right? This is -1, I2 is 0, I3 is 0, I4 is 0, I5 is this value plus 1 and I6 is the -1. This row and this column use this equation. Is it right? This indirectly, in this particular case, from these equations, we are preparing this matrix. And if I am arranging this equation in the compact form, this is QF into IB which is equal to 0. This is QF into IB which is equal to 0 because this matrix is very same as the fundamental cut-set matrix. -1 0 0 1 -1, I will go back. -1 0 0 1 and this -1 is that matrix. This is QF. This is IB, means QF into IB which is equal to 0. This is the row-wise addition. How is the column-wise addition? The column-wise addition will give the VB is equal to QF transpose into VC, where VC is this should be the VC. This VC is the cut-set voltages, that is Vx, Vy, Vz, which are the cut-set voltages. Is it right? And that's it about this row-wise addition and column-wise addition. This next part is the preparation of the cut-set matrix equilibrium equations. I will complete this part and then I will end for the today's lecture. This preparation of the equilibrium equation is not difficult. This figure means in this case it is assumed that each branch in the network will be of this format. Means having admittance followed by the current source. Agar hamara branch, if our branch consists of the impedance and voltage source, we have to convert this figure into this kind for solving the problems based on this cut-set matrix. Is right? Which we have followed the similar procedure in case of the reduced incidence matrix. If we are applying the KCL at node B, look at the KCL at this node B or this point, that is node X. This is node X. If we are applying the KCL at there, how is the KCL? Incoming current is equal to outgoing. This is incoming, this is outgoing, this is outgoing. Means IK is equal to this branch current, IK is equal to ISK plus I. IK is equal to I plus ISK or I plus ISK. For branch 1, this IK, K is nothing but number of the branch. For branch 1, this will become I1. This I is nothing but current in this branch. It will be current in this branch is given by the formula. This branch में current का formula क्या होगा? What should be the formula for the current? Voltage divided by the resistance or its impedance. This V upon Z will be the formula. What is the V? This V is nothing but VK, is nothing but V1. This V1 upon Z1. But Z1 is the impedance. We are expressing everything in terms of the Y1 or Y. That's why this can be written as V1 into Y1. V1 into Y1, where V1 is this voltage, branch voltage, and this Y1 is nothing but admittance of this branch, reciprocal of the impedance, which is 1 upon Z is nothing but Y. This V1 into Y1 is the current I1, this current for the branch number 1. Is it right? Similarly, this current will be ISK. K is nothing but branch number, IS1. In the similar way, for the branch number 2, it is I2 is equal to V2 Y2 plus IS2, and for the B branch, it will be VB YB plus it is ISB. And if we are arranging all these equations in the matrix form, this I1, I2, I3, I4, these are the branch currents, which is IB. Multiplication of this matrix with this, YB is the branch impedance matrix. This V1, V2, V3 is nothing but voltage matrix, and this IS1, IS2, ISB is nothing but the current matrix. Means all these equations can be organized in this particular format, and that can be named as IB is equal to YB into VB plus IS, and that we will call it as equation number 2. Equation number 2. But we know that the row-wise addition in the reduced incidence matrix is QF into IB is equal to 0. We are putting this equation number 2 in equation number 3. We are putting this equation IB. What is that IB? IB is this. I have tried to show here. YB VB plus IS. I will go back. YB VB plus IS is nothing but this is branch current, which is IB. The same thing which I have taken here. YB VB plus IS, which is equal to 0. Do the multiplication. QF into YB into VB. QF YB VB. This QF into IS plus this QF into IS, this multiplication, and this will be the equation number 4. This is the equation number 4. But from the column-wise addition of the reduced incidence matrix, we know that VB is equal to QF transpose into VC. That is cut set. VC is the voltage of the cut set. If we are putting this VB here, this QF YB, in place of VB, we are substituting this value. In that case, how will be the equation that I will discuss in the next slide? Here, this QF into YB into VB, and in place of VB, we are substituting its value as QF transpose into VC, because that value is QF transpose into VC. This is QF transpose into VC. And if we are simplifying this equation, this is QF into YB into QF transpose into VC plus QF into IS. I highlighted this. Why? Because this is nothing but the YC and known as cut set admittance matrix. This is the cut set admittance matrix, which is YC into this value, which is VC. This value I am shifting on the next side, means minus it is QF into IS, and it is the equation number 6. Means in this case, this equation is known as the equilibrium equation in case of the cut sets. This YC into VC, which is equal to minus QF into IS, and this equation is equation number 6, which is nothing but the equilibrium equation for the cut set, where this YC is cut set admittance matrix, and this value of the YC is nothing but QS YB into QF transpose. We have discussed the 3 methods that I want to conclude. First, we have discussed about reduced incidence matrix. We have the 2 things: column-wise addition, row-wise addition. How is the column-wise addition? VB is equal to A transpose into Vn, where Vn n is nothing but node voltages. A is nothing but reduced incidence matrix. This is transpose of that matrix. Its row-wise addition is A into IB, which is equal to 0, which is same as the KCL. And equivalent equation in this reduced incidence matrix method is Yn into Vn, which is equal to minus A into Is. This is the equilibrium equation. And in this case, this Yn is very same as A into Yb into A transpose. If I am coming to the next part, which is the type set matrix, which we have discussed. In this case, column-wise addition is Ib is equal to Bf transpose into IL, where IL is nothing but the loop current, or we can call it as IT, that is nothing but the tie set current. Is it right? Next is, it is Bf into Vb is equal to 0. This is KVL. Here is the KCL. A into Ib, Bf into Vb. This is KVL, row is addition. And in this case, equation is Z2 into IT, which is equal to minus Bf into Bs. And this Zp is impedance. Here is the admittance. Here is the impedance. With Bf into Zb into Vb, sorry, Bf transpose is the that value of Zt, and this is the equilibrium equation in that case. And finally, which we have discussed today, is this method, which is nothing but cut set matrix. This Vb is equal to QF transpose into Vt, sorry, it is Vc. This should be Vc, cut set matrix. Column-wise addition. Vb is equal to QF transpose into Vc. This QF into Ib is equal to 0, it is KCL. And Yc into Vc is equal to minus QF into I3. And this is equilibrium equation. And in this case, this Yc is equal to, our cut set matrix is equal to, admittance of the cut set matrix, our cut set admittance is equal to This is QF into YB into QF transpose is this method. Now look at last point. In this case, expected branch should be something like this. Each branch in case of the reduced incidence matrix should be something like this. This is the current, this is the admittance, this is YB, and here is the voltage VB. This voltage is the VB, this voltage is the VB, and this is current source. Must be in this format. In this case, each branch must be in this particular format. This has impedance ZB and it has voltage Vs. Maybe polarity something like this, or maybe reverse is the true. Means every branch in this case of the tie-set matrix should be represented like this, and we are considering this ZB. We are considering this ZB is branch impedance. Here it is YB, that is branch admittance. And finally, in case of the cut set also, each branch we are expecting something like this again, something like that. Means it should have, every branch should be represented in terms of the YB, VB, and this current IS, something like this. This is standard way, and that's it about this particular lecture. I will stop here.